The next section is on transformations of polygons. There are 4 basic types. Translation is when a polygon is moved. Rotation is when a polygon is twisted. And reflection is when a polygon is reflected or flipped over a line. Dilation is when a polygon becomes bigger or smaller, but the shape stays the same. So in thinking about this, think about which of these would keep the congruence or the shape the exact same size and shape, and then which of these would keep the same shape but not the same size. So similarity is the same shape, not the same size. Second, we realize all of are going to preserve similarity. So transition, reflection, and rotation, they actually keep the shape the same size. Dilation keeps it the same shape, but it doesn't keep it the same size. So it keeps similarity, whereas the rest of them do both keep it both similar and congruent. So let's look at examples of each. Here we're looking at a translation of a polygon. If we want to move 6 units to get to where this red triangle is, we have to think about whether or not we're moving up, down, left, or right. So if we follow each of these vertices over, we'll see we can move 1, 2, 3, 4, 5, 6 to the right in order to move the top vertice over to where the red triangle is. Now obviously we're going to have to move down as well. So we're going to move down 1, 2, 3, 4, 5, 6, and now we have moved our triangle to where the red triangle is. So what we would say is that the purple triangle has been translated to create the red triangle. So the 2 triangles are congruent. And in this picture they're showing a different vertice, but notice that all the vertices move together really 6 units right and 6 units down. Here's an example of a reflection. So to prove that they're congruent, we have to prove that the purple triangle is being reflected and then translated. So because it's not only being flipped upside down, it's also being moved. So it is being flipped upside down over the x-axis. So it's reflected over the x-axis. So if we look at the solution, it says reflect the purple through the x-axis, which means we flip it straight upside down. So we keep the vertices that are on the x-axis, we keep there, and then the vertices that are off of the x-axis, we move the same exact distance from the x-axis down below, and that keeps our polygon congruent. Then we're going to move all of these vertices over the same amount, so you can see it as a translation, or you might also notice that this is a reflection as well over the y-axis. So that's how they describe it, reflect the dashed purple through the y-axis. So again, in this case we're going to keep the vertice that's at 0, 0 in the same spot, but then we're going to reflect the vertice that's at 4, 0 over to negative 4, 0 and do the exact same thing with these vertices down at the bottom. Rotations of polygon is where we twist our polygon around. So in order to prove that these are congruent, we have to show that we've actually just taken this purple pentagon and twisted it. And typically when we talk about rotations, we're talking about how many degrees we have twisted it. So if we rotate red 90 degrees clockwise to create purple, or you can rotate purple 90 degrees counterclockwise to create red. I personally saw the purple as the main figure because it looks like more like a easy to look at a polygon, but it doesn't really matter. Now, a lot of times the degree measure they will talk about will be like 90 degrees, 45 degrees, 180 degrees, 360 degrees, would just take it right back where it started. So typically you'll see 90 or 180 degrees. So in this example, you're asked to find two symmetries of reflection. The hexagon has both vertical and horizontal symmetry, as you can see here. Also, each of its diagonals divides it into two identical halves, so it is symmetric about its diagonals. And here's a picture where you can see the diagonals without it being on either one of the axes. And then in the purple figure and the red figure, you can see how the figure can be reflected in several different ways. Symmetry of rotation. Find two symmetries of rotation. Well, in this figure, we were talking about rotation being usually 90 degrees, 180 degrees, 360 is a full turn, 270 degrees is 3/4 of a turn. So if we were to start with where it says 360 degrees, if we were to turn this 1/4 of a turn, this purple would go from top right to bottom right. If we were to go from 360 to 270, or to 180 rather, 360 to 180, that would be where we started with the purple top right, and then 180 is half a turn. So you can see the purple go from down at the bottom right over to the bottom left. And then if we were to create a 3/4 turn, which is 270 degrees, the purple would move up to the top left. And then if we come back to where we started, the purple would be at the top right. Dilations are where the figure changes how big it is, but it doesn't change the shape. So here's an example. We call these similar figures, where you have two figures that are the same shape but different sizes. And again, in this example, we have several transformations happening. We have a translation where we're moving the figure, as well as a rotation. So the figure was rotated 90 degrees. It translated 6 units to the right, translated 7 units down, and then rotated and translated together, keep the congruency of our parallelogram. Symmetry, there are several ways to talk about symmetry. One is symmetrical with respect to a line, which we saw a little bit before. Basically, we saw that in this slide. If you can take a shape and fold it in half, and the two halves line up perfectly, then the line that you folded upon is called the line that it is symmetrical upon. You can also have a shape that is symmetrical with respect to a point. And what that means is if you put a point within the figure, which is, it'll usually be the center point, and you then twist the figure, one point on the figure will eventually end up where another point on that figure started. So if I was to take this figure and twist it, that blue dot is going to end up where the red dot is. So that's what we mean by symmetrical about a point. So let's see if we can figure out if this is symmetrical about a point or about a line. So if I twist it around and it ends up like it started, that's symmetrical about a point. And that worked. Now, if I click on flip, and I say flip left, right, and it ends up exactly like I started, that would be symmetrical about a line. That did not work. Or I could do up or down, flip, up, down, and that did not work. So this one is symmetrical about a point. When I twist it around, it's symmetrical. Okay, we're going to do the same thing here. If I twist this, at no point does it end up looking like it did. So this is not symmetrical about a point. But if I was to, I bet you're starting to see this, flip this about a line, oh, you can't even tell I flipped it, but I flipped it vertically. So it's symmetrical vertically. Now if I flip it up and down, that's not going to be symmetrical, but it is symmetrical with a vertical line. And there's an activity that you can practice here at the end to help you get a hang of working with all the transformations.